Hello everyone, so my name is James Devine and I'm here today to talk on behalf of CosmicPi. I'll be talking about what our project is, the science goals we have, the hardware architecture of our detector, where we are right now with the development, and what we plan to do next. The objective of the CosmicPi project is to build fully open hardware cosmic ray detector that anyone with a reasonable degree of skill can either buy or build that can detect individual cosmic rays one at a time as they pass through the Earth, and it can be connected to a network to form a giant cosmic ray telescope, possibly the biggest cosmic ray telescope in the world. Some science background. So cosmic rays are continuously falling on the Earth from the distant regions of the universe. The ones we're interested in are called muons, it's a type of subatomic particle, and the ones we typically detect have a mean energy of 4 GeV for anyone with a physics background. That's not me, I'm an electrical engineer. What we're actually detecting is the secondary particles. So I'm going to take you through an example of what happens with an event reconstruction. Typically a high energy cosmic ray will hit the atmosphere, which is a bit like a protective umbrella around the Earth, and it will break up into lots of smaller, lower energy particles, which will then possibly even break up again. These are what actually reach us, and there are in fact many passing through us right now in this room. So the aim of our project is to make something that's open source, small, cheap, accessible, so that people can build a network. The advantage of this is that we can not only detect one cosmic ray, but we can detect a whole shower of cosmic rays, like you just saw. And if we have our timing correct, we will then be able to reconstruct at least part of the shower to effectively point a finger back into the universe to say the original piece of this cosmic ray came from over here, or over there. There are quite a few hardware challenges. It's obviously a completely hardware-driven project. In order to detect cosmic rays, we need a high stability, high voltage power supply, somewhere between 40 and 70 volts. We need very high gain on our amplifiers. 1/10⁶ is an absolute minimum. We need to generate a trigger so that we know when we've actually detected a cosmic ray, so we can trigger our analog to digital conversion. We need very high speed timing in order to be able to interface two boxes that are next to each other with a given offset. And we need to synchronize the ADC effectively to break up our time span of, say, 1 second into a number of buckets, so we can say that we have an event in this space at this time and in another space at another time, so that we can correlate the two to say that they're actually linked. And we have a lot of sensors to integrate as part of the overall science package. And all of this is going to have a USB plug on the end of it to plug into a Raspberry Pi. This is kind of the very high-level architecture that we have at the moment. So we have a detector module, which is a scintillator tile. It's a piece of plastic with a special chemical additive. It has 2 silicon photomultipliers, which are the detectors, and we have to put that in a light-tight enclosure. We have a fair amount of analog processing, so that's where we generate our trigger. We have our amplifiers, and we also shape the signal. The raw signal that we get out of the silicon photomultiplier is about 5 nanoseconds, so we have to lengthen that so that we can read it more easily. We then have quite extensive digital, well, for us, I think for you guys it's probably very basic, where we have an ADC, we read out a bunch of our other sensors, we organize that data into a packet in JSON format, and then we spit that out over USB to a Raspberry Pi, which then runs the rest of our data analysis stack. This is pictures of our hardware version 1, which we did about this time last year. This isn't actual size. The scintillator is probably about the size of a pen like this. And then here's our Pi hat. Again, it's the size of the Pi hat. This has been released under the CERN Open Hardware license, but it's not really ready to go yet. In terms of what's the structure, so we have the plastic slab, the scintillator package effectively, that's the mechanical part. Then on our Pi hat, we put a high voltage power supply, the analog front end, some sensor hardware, so we put an altimeter, temperature and relative humidity, and a GPS. The altimeter is there because we can't get good altitude resolution from the GPS. The temperature is there because it affects the performance of the silicon photomultiplier and the power supply. the relative humidity is there because relative humidity attacks the plastic scintillator. So over time, if it's in a high relative humidity environment, its performance will degrade. And the GPS is obviously to give us position, but more importantly, timing, so that we can manage to connect 2 or 3 or 4 or a whole network of different devices. In our first version, we implemented a hardware counter, so we had a 33 megahertz 32-bit counter that we just ran with an interrupt when we detected an event. This gave us some problems. All of this was connected via various buses, so we used SPI, I2C, GPIO, and UART to connect that to the Pi. And then we simulated having a central server to put all the data in. The lessons learned from this, the Raspberry Pi was far too slow for what we needed. We were looking at an event rate of around 5 Hertz, which for kind of real high energy physics is nothing, but for us it was still quite a lot. We found that we couldn't get the responses that we needed from the Pi just using standard Raspbian. The counter was poorly designed by me, and it limited our event rate to 1 Hertz. I hadn't considered that we might have one, more than 1 per second. We put a lot of effort into choosing our ADC, which wasn't really necessary, as I'll come on to later. And the power supply we used was too noisy, but that's kind of a suck it and see. We also didn't correctly match the analog front end to the SIPM. We've now moved on to version 1.1 as of this year. So we've taken a much more modular approach using dev boards for all the different bits of kit. And we're using electronics crate to do our analog, which is a standard in high energy physics to do this kind of thing. And we've also taken a much more stepwise approach rather than just spinning up a board from scratch. We're doing it piece by piece, one at a time, integrating both the hardware and the firmware that runs on our Arduino. Looking a bit more into detail on the analog side of things, so here we've got our the wiggly thing at the top is actually a wavelength shifting fiber optic embedded inside the plastic tile. So when a cosmic ray hits the plastic tile, it makes photons, which are green, and then they get captured into the wavelength shifting fiber, which turns the green ones into blue ones, again by some kind of chemical magic. And blue is matched to the acceptance curve of the SIPM. We then put this through amplifiers, we integrate the signal, and we use coincidence. So when we have a signal on both SIPMs, we know that we've got an event rather than noise. This is another very important aspect. This type of system is based on a real-world detector, for example Atlas or CMS, in very much miniature. We need the 2 channels. That's one of the things that dimensions the size of our hardware. As I said, the raw output from the SIPM is 5 nanoseconds, so we make that a bit longer so we can catch it with a pulse shaper, and we have a simple trigger to prevent us triggering all the time and actually looking at it in software, just to make our life simpler. Now we've moved on to a slightly different architecture, version 1.1. The scintillator slab is effectively unchanged. We're now using Arduino, and we're looking at making our PCB as an Arduino shield, with some augmented sensor hardware as well. We've added an XYZ magnetometer, full-effect sensor, and an accelerometer, which enables us to get the orientation of the system, so that we can actually see where the slab is in relation to the surface of the Earth. Because, for example, if it's on its side, the parameters of the cosmic rays arriving will be detected differently, because they'll have a different cross-section to the detector medium. And then we've put an Arduino DUE into our hardware at the moment. We have a 1 megasample per second ADC. We're using both channels of the I2C. We're using SPI to control the power supply, and the UART for the GPS, and then we use another UART over USB to put it into the Pi. We find this works a lot better. Things we were working on from version 1.1, we're having difficulty using a single core architecture to actually read in the events that happen randomly and split them out over serial without having it crash. We found the ADC, we did some testing. The one that's actually built into the Arduino DUE is perfect for what we need. It's just about enough to read the signal in. The key innovation we've done so far is setting our ADC into continuous read mode and then buffering it. So effectively this allows us to read back when we get an event. It probably sounds trivial, but it took us a very long time to come up with an idea of doing it like this. We're now working on the stability of the code. We can have it running for about 10-15 minutes, detecting cosmic rays the whole time at a rate of up to 5 Hertz. And finally, the other thing we've learned is that JSON is actually quite heavyweight when you're trying to get an Arduino to generate it and spit it out over USB. Here's a close-up of the slab. So as I said, it's an extruded piece of plastic. The reason we're using this instead of Geiger-Müller tubes or gas chambers is that when you built it, it's very stable, it's very repeatable, and it's very cheap if you build them in volume. On the outside, there's a titanium-based, it's titanium dioxide light reflective coating to ensure that any photons generated are reflected internally. The detector geometry is specific, so we will have a slab that's going to be our size for our box, probably not much bigger than a pi hat itself. And wavelength shifting fibre. This is our main mechanical component. So at the moment we're working on ways to make this an open source, an open design that people can build. Of course there are always going to be volume issues. You can't just buy one, you need to buy several thousand. The same for the wavelength shifting fibre. You can't make one in your shed because you need to buy several kilometres of fibre. We have a client for that too. Our current status, here on the oscilloscope you can see a cosmic ray which we detected with our prototype. The little peak on both channels shows that we got channel A and channel B, so we have coincidence. We last weekend integrated the Maxim Boost IC, which is a very stable high voltage power supply which we're using for the SIPM. The rack that I showed you earlier still has all our analog in it, so we're moving that from a 19-inch rack to PCB is our next challenge. Along the way, we've invented an open data format for cosmic ray exchange as part of the Mozilla Science Sprint, which is very handy because it kind of gives us something to aim for and it helps us to interact with everyone else. We're not the only people trying to build a network of cosmic ray detectors across Europe. It would be great if we could exchange our data. And we're working towards our prototype version 2. So what's next for us is to make a fully integrated prototype on a single board, check the robustness of our firmware and test it kind of over a period of days and weeks. We need to work on our software stack on the Pi, and open sourcing the scintillator design is something we're looking at the moment. And then we hope to put the whole thing into production. So, like a lot of open source projects of this type, we're thinking about crowdfunding. We've already had some contact with Kickstarter. We're planning to go for production on Kickstarter and then to fully open source all of it, particularly the mechanical parts of the scintillator, afterwards. So that's all we do. Any questions?
I was wondering, you want to spread out a large number of sensors. Do you have some kind of target price for the hardware, or what are you thinking of?
Our target price is at the moment around $300 per pixel.
Can you tell us 2 or 3 words about the origin project? I mean, how it came up with an idea?
So the project, it actually started here at CERN 3 years ago with a hackathon called the WebFest, where we were in touch with a network of people doing exactly this based on Geiger-Müller tube detectors based in Florida. And we got in touch with them before and we got them to send us a prototype, which we thought, oh, this is very clunky, and they have like a custom PCB that's kind of almost the size of a pizza. We thought we can probably do better than this, or maybe we can optimize it. So we hacked that and we used an Android phone to do the GPS, the timing, and all of the other sensors, and also the data transmission to send it to a database. We were using a USB interface to Android, which I don't know if anyone's used it. I would definitely not recommend that as an API. I think it's more or less abandoned. And we decided at the end of the project, we had a proof of concept, but the way of plugging in over USB was just too horrible, and we decided to park it. And then a year ago, someone from the used to work in our IT department, Francois Gray, came and tapped me on the shoulder and said, what about that project you did 2 years ago? Why don't you have a new look at it now that you have new hardware available and technology's moved on? And that's when the CosmicPi started up.
Was that a banana?
Yes, yeah, there were several bananas in the presentation, which we use for scale, so you can see how big they are. We also have one in our rack. We had one in the first presentation we gave, and it kind of stuck in all our photos. Is it the same banana? No. No, we're on to many versions of our banana.
Hello. I presume it can only detect particles that hit the box and just in the sensor. But if they are so dispersed all over the place, how do you know it's the same particle you're registering?
So that's where the timing resolution is key. Maybe if I go back to the shower. So the theory, or the current understanding of how high energy cosmic rays work is that when they hit the atmosphere, they create a shower. And what we're interested in is detecting those showers. So you have lots of particles traveling at basically the speed of light that come down in a cone. And the focal point of the cone is the origin of the interaction with the high energy particle. So if we have enough detectors over a small area, then we can pick up enough pieces to actually put together the whole thing. That's not to say that we will capture every single piece, but we will capture enough to give us a representation.
How many particles does it give in this shower? Is it in the tens or in the millions?
I have no idea, but it's enough that we could capture them if we had. I think the calculations we did had about 20 detectors over kind of the Geneva area, and now within a period of a couple of months, we would be able to reconstruct a few showers. I would imagine it's in the millions, at least.
What resolution time do you need? What resolution time do you need to be able to reconstruct it?
So the target timing resolution we have at the moment is 300 nanoseconds. So being able to break a 1 second, which we get from the Navstar GPS, into 300 nanosecond blocks, and then tagging each event within that. And then we can take the distance that we know between the 2 points, multiplied by the speed of light, and triangulate effectively. In practice, we haven't yet reached that with our hardware implementation. We're looking at using the U-Blox Neo, it's the Neo 6T, which is a GPS chip that has an integrated timer, and you can send an interrupt when you have an event, and then read back over UART what the index is, and that has very precise time resolution. Sorry?
What's the jitter of the GPS?
Good question. I'm
That would
afraid
be quite interesting.
I don't know. For the Neo 6T, we're looking at tests that were actually done by the guys at Ergo, who are looking at moving to that as well.
Well, thanks, James.